Welcome. In this lecture, we are going to work through the small signal mid-frequency analysis of the common emitter amplifier using the h-parameter model. By the end of this session, you will be able to represent a bipolar junction transistor with a simple two-port network and use that network to calculate an amplifier's current gain, voltage gain, input resistance and output resistance. This first section builds the tool we need before we can analyze any amplifier, the h-parameter model of the common emitter transistor. We will derive the 4 h-parameters from first principles and then draw the small signal equivalent circuit they define. Once we have that model, the next section will put it to work analyzing a complete amplifier stage. Let us start with 3 ideas that frame everything that follows. First, when the emitter to collector voltage and current only change a small amount around their steady operating point, what we call the Q point or quiescent point, the BJT behaves almost linearly. That means we can replace the transistor with a simpler linear two-port network made up of impedances and control sources. This is called a small signal equivalent circuit model, and it is the whole idea behind today's analysis. Second, we are going to work in the mid-frequency range. This is a band of signal frequencies that is high enough that the coupling and bypass capacitors in the circuit behave like short circuits, but low enough that the transistor's own internal capacitances behave like open circuits. In this window, capacitors essentially disappear from the analysis, which is what makes mid-frequency analysis so much simpler than low-frequency or high-frequency analysis. Third, in practice, designing a small signal amplifier is a two-step process. First, you set the DC bias or the Q point. Then separately you determine the voltage gain, current gain and impedance values at signal frequencies. Today we are focused entirely on that second step. Now let us build the model itself. In the amplifier configuration, there are different ways to define a set of h parameters depending on which transistor terminal emitter, base or collector is shared between the input and output of the amplifier. We are going to use the common emitter configuration. For this configuration, we treat IC, the collector current, and VBE, the base to emitter voltage, as dependent variables. That means we write VBE as some function of the base current IB and the collector to emitter voltage VCE, that is shown here as VBE equals F1 of IB and VCE and IC equals F2 of IB and VCE. Now here is the key small signal idea. If VBE only makes small excursions around the Q point, we call that small change VBE in lowercase, and the corresponding change in collector current IC also lowercase. Applying the chain rule to this function gives us two equations, one for VBE in terms of partial derivatives with respect to IB and VCE, and one for IC in the same form. These 4 partial derivatives evaluated right at the Q point are exactly the 4 h parameters we are about to define. Each of the 4 partial derivatives from the previous slide has a name and a physical meaning. AHIE is the input resistance, the partial derivative of VBE with respect to IB holding VCE constant. It tells you how the base emitter voltage responds to a small change in base current. HRE is the reverse voltage ratio, the partial derivative of VBE with respect to VCE holding IB constant. It captures how much the output feeds back into the input, usually a very small effect. AHFE is the forward current gain, the partial derivative of IC with respect to IB holding VCE constant. This is the parameter most of you already know informally as beta, the transistor's current gain, and HOE is the output admittance, the partial derivative of IC with respect to VCE holding IB constant. It is the reciprocal of an output resistance. Notice the units do not match. HIE is a resistance, HRE and HFE are dimensionless ratios, and HOE is a conductance. That mismatch in units is exactly why these are called hybrid parameters. These 4 H parameters let us draw a complete small signal equivalent circuit for the transistor, valid as long as the signal excursions around the Q point stay small enough that the H parameters can be treated as constants. On the input side, between base and emitter, we have a resistor of value HIE in series with a voltage controlled voltage source HRE times VCE. That source represents the small feedback from output back to input, accounting for the early effect. On the output side, between collector and emitter, we have a current controlled current source HFE times IB in parallel with a resistor of value 1 over HOE. That current source is the heart of the amplifier. It is what turns a small base current into a much larger collector current. This 4-element network is the model we will now use to analyze a complete amplifier stage. With the transistor model in hand, let us analyze a real amplifier stage. The figure shows a basic common emitter amplifier drawn without its DC biasing circuit, just to keep things simple for a C analysis. We are going to determine 6 quantities. First, the current gain AI, defined as the output current I/O divided by the input base current IB. Second, the input resistance Ri, defined as VB over IB, the resistance seen looking into the base. Third, the voltage gains AV, defined as VO over VB, and AVS, defined as VO over Vs, which additionally accounts for the source resistance Rs. And finally, the output resistances Ro and Ro prime, where Ro prime takes into account the effect of the collector resistor Rc. To analyze this circuit, we redraw it as its a C equivalent. The transistor is replaced by the H parameter model we just built, and the coupling capacitors along with the DC supply VCC are replaced by short circuits, since at mid-frequency they don't affect the signal. All the voltages and currents from here on are the RMS values of the AC signals. Let us find the current gain AI first. By definition, AI equals IO over IB. Since IO equals minus IC, we can write IO as minus HFE times IB minus HOE times VCE, and because VCE equals IO times RC, substituting that back in and solving for IO over IB gives a clean result. AI equals minus HFE divided by the quantity 1 plus HOE times RC. Notice the negative sign is already appearing here. That is our first hint of the amplifier's phase inversion. Next, the input resistance Ri, defined as VB over IB. This is what you would measure looking into the base terminal. Writing KVL around the input loop gives VB equals HIE times IB plus HRE times VCE. We already know VCE equals AI times IB times RC. From the current gain result, substituting that in and dividing through by IB gives Ri equals HIE plus HRE times AI times RC. Physically, this says the input resistance is mostly set by HIE, with a small correction term coming from the feedback parameter HRE. Now, the voltage gains. A V is the ratio VO over VB, and AVS is the overall gain VO over Vs, which includes the effect of the source resistance Rs, since VO equals IO times RC and IO over IB is AI. We get AV equals AI times RC over Ri. For AVS, we bring in a voltage divider between Rs and Ri at the input. Vb over Vs equals Ri over the sum of Rs and Ri, and combine it with Av to get Avs equals Av times Ri divided by Rs plus Ri. There is a useful rule of thumb here. If Rs happens to equal Ri, then Avs is exactly half of Av. In other words, half of the input signal voltage is simply lost as a drop across the source resistance before it even reaches the amplifier. Finally, the output resistances Ro and Ro prime, what you would see looking back into the output terminals without and with the collector resistor Rc included. To find Ro, we set the source voltage Vs to 0, but keep Rs in the circuit and treat Rc as infinite or open. Writing KVL around the now source free input loop gives an expression for Ib in terms of Hre and the test voltage V2. Substituting that into the output loop equation for I2 gives us the short circuit admittance Yo equal to Hoe minus Hfe times Hre divided by Rs plus Hie. Since Ro is simply 1 over Yo, we now have a complete expression for the output resistance. And if we do want to include Rc, the more realistic output resistance Ro prime is just Ro in parallel with Rc. Let us put everything together. This slide summarizes the complete set of design formulas for a common emitter amplifier, Ai, Ri and Av on one side and Avs and Yo on the other, everything we derived over the last several slides, now in one place for quick reference. From these formulas we can state 6 general characteristics that make the common emitter amplifier so widely used. It gives a large current gain, a large voltage gain, and therefore a large power gain, the product of Ai and Av. It introduces a current and voltage phase shift of 180 degrees between input and output, and it offers moderate input impedance and moderate output impedance, which makes it easy to connect between other stages. This combination of high gain and moderate, well-behaved impedances is exactly why the common emitter configuration is the default choice for a general purpose amplifier stage. Let us finish by working through a complete numerical example using the formulas from the previous slide. We are given the H parameters of a transistor in the common emitter configuration. Hie equals 1 kilo ohm, Hfe equals 100, Hre equals 2 times 10 to the minus 4 and Hoe equals 20 microamps per volt. The collector resistor Rc is 5 kilo ohms and the source resistance Rs is 1 kilo ohm. Our job is to find AIR, IAV, AVSRO and Ro prime. Starting with Ai, minus Hfe over 1 plus Hoe times Rc gives minus 100 over 1 plus 0.1, which works out to minus 90.9. Next Ri, Hie plus Hre times Ai times Rc. Substituting numbers, 1 kilo ohm minus 2 times 10 to the minus 4 times 90.9 times 5 gives 0.909 kilo ohms. Then Ai times Rc over Ri, which comes out to minus 500. And just like before, that negative sign tells us there is a 180 degree phase shift between the input and output voltage waveforms. Avs brings in the source resistance, Av times Ri over Ri plus Rs, giving minus 238.08. For the output side, Yo equals Hoe minus Hfe times Hre over Hie plus Rs, which works out to approximately 10 times 10 to the minus 6 Siemens. Taking the reciprocal gives Ro equal to 100 kilo ohms. And finally, Ro prime. Ro in parallel with Rc comes out to 4.54 kilo ohms Notice that this example reproduces exactly the 6 characteristics we listed a moment ago: a large current gain of about 91, a large voltage gain of 500, a full 180-degree phase shift, and moderate input and output impedances. That is the common emitter amplifier working exactly as the theory predicts. Solve more exercises given in textbooks to gain a better understanding. To make sure our hand calculation was not just internally consistent but actually correct, we cross-checked it against a circuit simulator, LTspice. Rather than using a generic transistor model, we built the exact H parameter equivalent circuit from earlier in this lecture directly as a linear netlist, a resistor for HIE, a dependent voltage source for HRE times VCE on the input side, and a dependent current source for HFE times IB in parallel with a resistor equal to 1 over HOE on the output side. Because this netlist uses only the 4 H parameters, not a full transistor model, the simulation is exact, not an approximation. 3 separate .op or operating point simulations were run on this circuit, one on the main circuit with the source and collector resistors in place to get AI, RI, AV, AVS and the power gain, and 2 more on modified versions of the circuit with the collector resistor removed and then with it included, each using a 1 amp test current injected at the collector node specifically to extract the output resistance. Here is the result. Every quantity we calculated by hand on the previous slides placed side by side with what LTspice actually computed from the netlist. Current gain, input resistance, both voltage gains, power gain, and both output resistances, all 7 match. The current gain comes out to minus 90.9 both ways. The voltage gain without source resistance is exactly minus 500 in both columns. And notice the output resistance row, 100 kilo ohms without the collector resistor and 4.76 kilo ohms with it, both confirmed by simulation. This kind of agreement is the whole point of building the exact H parameter netlist rather than trusting a generic model. When hand calculation and simulation agree to 4 or 5 significant figures like this, it tells us the formulas are correct and were applied correctly, not just that the simulator ran without errors. So what does this verification actually tell us beyond just confirming arithmetic? First, the phase inversion here is exact, not approximate. For this particular transistor, HIE times HOE minus HFE times HRE happens to equal exactly 0. So the general voltage gain formula collapses neatly to AV equals minus HFE times RC over HIE, giving exactly minus 500, and that is precisely what both the hand calculation and the simulation return. Second, this confirms why source resistance matters so much. RS and RI form a voltage divider at the input with a ratio of about 0.476, which is exactly why AVS at minus 238.1 is roughly half of AV at minus 500, even though the current gain AI doesn't change at all, since it's defined right at the amplifier's own input port before that voltage divider. Third, this confirms how output resistance behaves. Once you connect a real load, on its own the transistor's output resistance is very high, 100 kilo ohms. But as soon as you connect the 5 kilo ohm collector resistor in parallel, the combined output resistance drops to 4.76 kilo ohms, much closer to RC than to the transistor's own resistance. RC simply dominates that parallel combination. Taken together, this simulation doesn't just double check our arithmetic, it validates that the H parameter model itself and the formulas we derived from it correctly predict how a real common emitter amplifier behaves. With this last slide, we complete this lesson. Thank you.